Welcome to the 11th session of the FDP, Recent Trends in Power System Operation and Control. Today I would like to welcome our speaker, Dr. Professor Archana Thosa ma'am. Ma'am has completed her B degree in 1992 from Walchand College of Engineering, Sangli, ME Electrical from Walchand College of Engineering, Sangli in 1997, PhD degree. Sorry, ma'am. PhD degree in 2009 from IIT Kharagpur. Ma'am has been awarded with National Merit Scholarship in 1986, selected by the National Productivity Council India and Asian Productivity Organization Tokyo, Japan to represent the India on evaluation of training effectiveness. Received first prize for feedback by Bureau of Energy Efficiency. Received first prize for the project guided to UG students on portable bio plant by TCS. Received consolation prize for the project guided to UG students on Green Village by TCS. Madam research area included special machines, fault tolerance control, non-linear control system, renewable energy, energy minimizing control, DC-DC converter designed for charging applications, H infinity control. So I would like to welcome Madam. Welcome, ma'am.
Yeah, thank you very much for a nice introduction. And shall we start the session?
Yes, ma'am. Yes.
Okay. So to get a better bandwidth and there should not be any interference, I will switch off my video after some time. And very good afternoon to each one of you, dear participants. And today I will be covering the facts basically, the flexible AC transmission systems and controllers. So I will be introducing to you various types of fax controllers and the control schemes, control systems related with that particular fax controller. Okay, so I will share my screen now and I will start the session. So before that, I would like to do one thing, like what are your expectations from the session? I would like to know that what are your expectations from this session, and like please you can write in the chat box. So I will see into the chat box what you have written. So what do you expect from this session? Because this is the 11th session you had said, and you all might be working in a power system domain and might be working with some fax controller, may have implemented it in a MATLAB or in a practically also. I do not know the background of the participants. So can you write down in a chat box like what is expected out of this session? What is your expectation, or what you are expecting that this session should give it to you? So please write in the chat box quickly. So research topics in multifunctional fax, scope for research. Okay, so you all are looking for the research, right? So the basically what is said is that you are more interested into the research. Okay, so I will try to give you some research inputs, like you can take you can take your research further, but at the same time the basic concepts and the basic knowledge is also important, which I would like to now do it through this session. So I'm sharing my screen right now, and just tell me whether it is visible or not. So could you see my paintbrush paint screen?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, thank you. So we will first understand what is the need of a fax controller, right? Or what is the need of a flexible AC transmission system in the country like India, and then so I will be doing some little bit mathematics. That's why I am using a slate. and then we'll go to the, we'll see the various types of fax devices and controllers. Okay, so the first of all is that you know that its name is a flexible AC transmission system. So its name itself tells us that what does it mean. So it tells us that there is an AC transmission but which is flexible. There is a AC transmission which is flexible. So the other uses of this is for a reactive power compensation, or it is other uses is for the power factor improvement, or the other use of this flexible AC fax controller basically is to mitigate the PQ issues. So these are the broad other applications, broadly the other applications, okay, broad areas of other applications. But basically this is actually designed for flexible AC transmission system. You know who is a pioneer? The pioneer is a Hingorani. So he has developed the system, who is the basically Indian origin scientist, and he has introduced this researcher, and he has introduced this flexible AC transmission system, a novel concept to maximize the power transfer. Now the same system, as I said, can be used for reactive power compensation wherever required, for the power factor improvement, or to mitigate the PQ issues like the sag and swell. So whenever there are equipments like the huge machines and all, 1 second, no? Only 1 second. Hello. मैडम मेरा 1 से 3 तक लेक्चर है, कर दो अभी. Okay. Please excuse me for 1 minute. Okay, sorry. Sorry for some technical issues. So now we will start, like we'll first set up the context why we should go for a flexible AC transmission system. So it is introduced by Hingorani, the great researcher in power system, and it can be used for reactive power compensation. It can be used for a power factor improvement. It can be used for dealing with the PQ power quality issues like a sag and swell. So whenever there is a requirement of mitigating these issues, these fax controllers have proven very well. The performance of the fax controller was good. So we will see by one equation, that is the power transmitted is given by the Vs, Vr by X and sine delta. So if you want to maximize this, then you have to increase. You can increase mathematically. If you look at it as an equation, you can make the delta is equal to 90. So the power transmitted will be maximum. That is the one case. You can increase the sending end voltage. You cannot increase the receiving end voltage, but you can decrease the X. That is the reactance of the transmission line. So these are the three parameters which you can basically modulate, or you can change so that the power transmitted over the transmission line will be maximized. Okay. So what happens actually, the country like India or any country in a power system, there is a generation and the demand. So generation and demand. So there should be a matching between the generation and demand, and this cannot be done every time because always the demand is more and the generation is less. And on the other side of it is that you require a huge transmission line network. You require a huge transmission line network, and this transmission line network to transmit the power from generating to the demand also involves lot of issues like a land. So first of all, whenever it is to be laid down, the transmission line structure, the land is a big issue, and you have to, the farmers has to compromise it. Even if the plants below the transmission line, if we can do some farming near the transmission line, passing to the tower, near the towers and all, as per the safety rules. Still, there are a lot of research which is telling us that yield gets affected. Okay, so the land is a big issue, the cost is big issue, and even the losses, which is important in terms of electrical engineer, for the electrical engineer, the losses are huge. So these losses makes that the transmission line efficiency, or you can say the maximum power capability of transmission line reduces. So this is an issue with the power system. Hence, now you may be knowing that people are going for a microgrids and even the nano grids and all, because this avoids the huge transmission system network. But you cannot simply depend upon the microgrids and nanogrids. This can be an appropriate solution for the rural areas or the areas where there is a tough terrain and you cannot install the transmission line. There it can be given a thought of microgrids and nanogrids. Now, a few people might be thinking that why the rural areas? Because the rural areas requirement as per the electricity or as per the electrical power is relatively less. So you can have a small village which will be powered through the microgrids or nanogrids. Then the transmission line losses are important, is huge, and that is a significant factor which is to be considered. The other factors which you have seen that is the impedance of the transmission line. So the impedance of a transmission line, that is the reactance of a transmission line, it will vary with the current carrying capacity and the conductor size. So these all have initiated to think upon what should be a solution which will give us the maximum power transfer over the transmission line, because we can do that much only, that we can increase the efficiency of a transmission line. So Ingorani has suggested that we can play with this X. So we can reduce the X. But for a huge transmission line, adding permanently some reactive compensating element into the transmission line will not help us, because there will be a continuous losses, and then the switching of those devices will be required, and the permanently if we keep, then the reactive power demand also changes. So as the reactive power demand changes, the permanent installation of any reactive element on the transmission line will not solve the purpose, but it will on the other side it may create a problem also. So what is the solution then? So you have to reduce this X by introducing some controller into the transmission line. Okay, so with some controller in the transmission line, you can reduce this X. How do you reduce this X? By creating a situation wherein the reactive power is injected into the line. Okay, so we will just see how some systems look like. Like suppose this is the one generating station, and then connected. There is another generating station connected to this. There's a one transmission line going on, and there's another transmission line going on. So this is connected like transmission line. The impedance of this is equal to X, for example. The impedance is X. This line of impedance is twice X. It's more. So the power capability will be 2/3 here. The power capability will be 1/3 here. So you know that this impedance affects the power transfer capability. Now there was another solution came in between. That is, this line is like this, suppose. But the another solution is that you can have a HVDC system. So HVDC means there will be converter at this end, and there will be converter at the other end. So you can have this system. So this is another way to maximize the power transfer capability, because now the power flow will be as desired. So now the power flow will be as desired. So this is one of the option. So this is like this converter. So this is one of the option. The another option which Ingorani suggested is that have something which will be something like this, wherein the reactive element is variable. Where the reactive element is variable, it will not be a constant. Obviously, these are all connected to the load. These all are connected to the loads. So find out something which is the variable reactor kind of a thing. Okay, variable reactor kind of thing. So that is the suggestion by Hingorani, and that is called as a flexible AC transmission system. So a fixed capacitor or a fixed reactive element will not be introduced into the line permanently, but it will be a variable. And where to put it, not at the load side or not at the source side, but the location is also mathematically proven where it is to be introduced. Okay, we will be looking at it through our as we proceed into the session. So this is one of the thing which is which gives the birth to the facts technology. Then the next is, you can also a little bit go ahead, and this is one generator, again the load, and you can have the variable phase angle. So you can have not only the reactor is the reactors is changing, but the variable phase angle is also changing. So you can introduce that also. So with this, you will be transferring a power. You will be transferring a power as you desire. So power transfer as per desired. So this is a power transfer as per desire, as desired. So these are the two things which was introduced, which is actually called as a fax controller. So I think with this we have enough discussed about the why we need a fax controller and what does it actually mean. We'll go step by step. Is there any question?
Yes. How phase angle will be varied, ma'am?
Could not hear you, sir.
Phase angle, how to vary, ma'am?
Yeah, phase angle can be varied by introducing the again the reactive elements into the circuit, or a transformer with a transformer, phase angle changing transformer. Phase angle regulators. Okay, we will be coming to that, sir.
Can you please explain a little bit more, ma'am?
Yes.
Please, can you please explain a little bit more, ma'am, if it's possible?
Yeah, I will come to that point. We will be coming to that.
Ma'am, why this is not flexible?
Why this is?
Flexible.
Because you can transmit a power as per your desire. Okay. So you look at this. We are more focusing on this fax controller. So here what is it? It is the variable x, which the reason mathematically, the reason I have given you is that the power transmitted is by this formula, which is a very common. So if I change this, if I vary this, then obviously the active power transmission over the line is going to maximize. Okay, you can increase it, I mean. So with this variable reactance, you can transmit the power as you desire. So the control, it is a controllable. So you can maximize it. So as you proceed, you will understand how the control system helps to do this. Is it clear? So now what has happened? You know that whenever there is some concept comes into the practice, then you have to define it with standard. Okay, because otherwise what will happen? As the name is a flexible, the people will do lot of flexibility and will not be able to achieve anything. So it has to be defined in a standard way. So the IEEE has given a definition of flexibility of electric power transmission is the ability to accommodate changes in the electric transmission system or operating conditions while maintaining sufficient steady state and transient margins. Okay, so you do the changes, you make the flexible, but your steady state and transient margins need to be maintained as per the norm. Then the flexible AC transmission system, the other definition is alternating current transmission system incorporating the power electronic best and other static controllers to enhance the controllability and increase the power transfer capability. Okay, so this is the most popularly used definition. The second definition is most popularly used. So if you look at this definition, you will understand that if you want to do something in a fax, then you should have enough knowledge about the power electronics, then the control system, and obviously the power system, because it is dealing with the power transfer capability, right? So this is very popularly used definition. So this subject is a combination of a power system, control system, and the power electronics. So the general symbol for the fax controller is shown like this. As just now I have said, it's a power electronic base. So it is some power electronics element has been shown in the block diagram. So this is the general symbol of fax controller. Now, what do you mean by fax controller is again given by IEEE is a power electronic base system and other static equipment that provide control of one or more AC transmission system parameter. Okay, so this whenever any controller which is doing this thing, then you can call it as a fax controller. So what are the parameters which are driving this change? So I have already explained you that the impedance, the line impedance is very important, which you can change. Then when the angle is not large, then the control of X or the angle sustainability provides the control of active power. So similarly, injecting a voltage in series with the line perpendicular to the current flow. So when I am saying that a voltage injection in series with the line and perpendicular to the current flow, what does it mean? It means that I am introducing some reactive power into the circuit, because whenever there is a quadrature relationship, it indicates that it may be a positive reactive power or a negative reactive power. So injecting a voltage in quadrature is like a mimicking the concept of introducing the reactive power in series. Then in line with any phase angle with respect to the driving voltage can control the magnitude and phase of the line current. So you can now understand. So quadrature will give you one thing, even with any phase angle with respect to the driving voltage, will give you the control over the reactive power injection. So this will precisely control the active and reactive power flow both. Okay. So this is one thing. And when the angle is not large, the controlling the magnitude of one or the other line voltages can be very cost effective, means for the control of reactive power flow through the interconnections. So these are the some parameters by which you change will give you the maximum power transfer over the transmission line. Now, as I said, that it involves the power electronics, it involves the converter, and also involves the control and the power system. So can we take your questions at the end of the session?
Okay, ma'am.
Can you please write it down? And if it, so that you can delete the irrelevant questions and keep the relevant questions, and we can have the discussion at the end of the session. So that will help me to go in a flow. Is it okay? Hopefully. So these are the devices which are used. So I already said that it's a power electronics, control, and a power system combination. So power electronics involves many devices. So this all of you know that diode, transistor, then insulated gate bipolar transistor. Then what is this? Any one of you? Any one of you can tell what is this?
MOSFET.
Yeah, MOSFET. Then this is Thyristor.
Thyristor.
This is GTO.
GTO.
GTO. Then this is
No idea.
MCT. Then this is ECT. And this is something extension of MCT. Okay. So these are the MOS control. Means MOS control thyristor, MOS capacitor control thyristor, and this is what you call it as a the gate turn off. MOS and gate turn off. So combination of both. So these are the some devices which are used as a devices in the converter in fax system. Okay, so you have to you should have a knowledge of this devices correctly. Then only you will be able to select the correct devices for the application. Now, how will you select the device? The device will be selected by the power requirements for the gate, then di by dt capability, dv by dt capability, because you know that in converter, the devices will be switched on and off continuously. So the switching frequency will be very high. So when there is a high switching frequency, you have to consider the di by dt and dv by dt ratios. Then turn on and turn off time, then turn on and turn off capability, which is expressed in terms of a SOA. Always we look at the self-operating area, uniformity of characteristics, because you will be using, suppose, a bridge of 6 devices, then all the 6 devices should have almost same characteristics, quality of starting silicon wafers, the class of a clean environment for manufacturing of devices, etc. So these are the few parameters which is to be looked while selecting the devices for doing the controller, like making a converter. So the converters are basically of 2 types. One is called as a current source converter, and the other is called as a voltage source converter. So in a current source converter, the direct current always has one polarity, and the power reversal takes place through the reversal of a DC voltage polarity. And in voltage source converter, the DC voltage always has one polarity, and the power reversal takes place through reversal of a DC current polarity. Okay, so basically when you consider a current source converter, so any converter, you can consider it as a 2-port kind of a network. So input and output. Okay, so in a current source converter, the input is inductor. At the input side, there will be inductor, and output, now as a part, output should have a capacitor. Okay, so in a current source converter, what happens? The inductor is used, so you have to obviously use some additional capacitor at the other end. So that is one drawback of the current source converter. In a voltage source converter, what happens? On the input side of a voltage source converter, there is a capacitor, and because it's a voltage source, so the voltage source has to be created. So there will be a capacitor, and at the output side, you need a inductance. If you look at the 2-port network theory, so you need a inductor at the output of the voltage source converter, and this inductance is obviously provided by the transformer which is connected to the other side, or the any reactance coming into the path. So what happens? The inductance requirement is quite a lot automatically taken care. Hence, the voltage source converter is always preferred over the current source converters. So a lot of research is also going on how to incorporate current source converter by making it more efficient. But till now, it is seen that we always prefer voltage source converter over the current source converter. So the reason is that the voltage source converter topology itself gives you a lot of benefit in terms of the inductance at the output end. So there are some benefits from the FACS technology is that control of power flow as you desire, increase the loading capability of lines to their thermal capabilities, including short-term and seasonal. So you know that the loading of what parameters limits the loading of line. So there are 3 parameters which limits the loading of a line. One is a thermal, then dielectric, and stability. So you know that when the line is overloaded or it is loaded to the extent it will get heated. So the line should have that capacity to withstand that temperature. Then the dielectric means like from an insulation point of view. So whenever there's a high voltage is passing, so it should withstand that. And the stability will be in terms of transient stability, dynamic stability, steady state stability, frequency collapse, voltage collapse, and the some resonance issues. Okay, so these are the things which governs the loading capability of a line. Okay, so increase the system security through raising the transient stability limit, limiting short circuit currents, overloads, managing cascading blackouts, and damping electromechanical oscillations of power systems and machine. provide secure tie-line connections, provide greater flexibility in string, in setting new generation, then reduce reactive power flows, and increase the utilization of lowest cost generation. So these are all the benefits you can see from the fax technology. Now we'll come to the various types of controllers. So there are 4 types of a controller. One is series controller. The fax controllers are classified as the series controller, shunt controllers, combined series controller, and combined series shunt controllers. Okay. So basic types of controllers are like a series controller. First we will see. So series controller means the controller, this is fax controller representation, will be connected in series with a line. Will be connected in series with the line. So this is a variable reactance. You can understand it. This is a variable reactance. So what will happen by varying the reactance of this, automatically the line reactance will also change. So with this, you will increase the power transfer capability. In a shunt controllers, you will be putting it parallel like this, and the injected current will be in phase quadrature with the line voltage. Okay, so the shunt controller will look like this. Then in a combined series controller, there will be one converter in series, another converter in series, and their DC link will be tied together. So their DC link will be a common. So this is called as something interline power flow controller. Okay. Then the next is the combined series and shunt controller. So now here one controller is connected in series, the another converter is connected in like a fax controller or a converter, anything you can say, connected in parallel to the line, and this has been like now coordinated by a single converter, a single controller, I mean, and hence it is taking the benefit of both the series and the shunt controller. I think somebody's mic is on. Will you please mute the mic? Will you please mute the mic so it will not create any disturbance also? So this is the combined series and shunt controller, which is called as a unified power flow controller. Why it is called as a unified? Because here these two controllers are unified. They are tied together by this coordinated control. So hence it is called as a unified power flow controller. Now the shunt connected controllers are of various types, like a Thyristor controlled and Thyristor switched reactors, then Thyristor switched capacitor, then fixed capacitor Thyristor controlled reactor type var generator, then Thyristor switched capacitor Thyristor controlled reactor type var generator, and a static synchronous compensator. So all these, the upper 4 are of the type of impedance changing controller kind of a thing, where you will be changing the impedance of the fax controller, impedance of the line, and this one is called this blue one StatCom. It is called as a switching type of a controller. So there are 2 types. One is the impedance changing, and the other is the switching kind of a thing. So variable impedance type, basically these are all the static var generators. These are all the static var generators. So they are generating the var, the variable, the reactive power, and this will be, these all 4 will be doing it by varying the impedance, whereas this will be called as a switching kind of a thing. So these are the 2 types. Now we'll see one by one how does it work. So this is basically another point will come to your mind is that where should I place this fax controller? Now I have selected that I will go for a shunt type of a controller. So I will be connected it in parallel to the line. So I will be injecting a current which will be in phase quadrature to the voltage, and thereby I will be mimicking the reactive power compensation. So now I will see where should I keep this, fax controller. So the best point is the midpoint location. So best is the midpoint. So midpoint is best because at the midpoint the sag of transmission line is also more. Okay, so it is seen that it is observed that the best location to put the fax controller is at the midpoint of transmission line. So this is a transmission line. It is divided into two halves, and the fax controller will be introduced here at the midpoint. Okay, so the mathematically you can prove that by putting a fax controller at the midpoint of a transmission line, how it is helpful. So now mathematically, if we solve this, like this is a sending end voltage, receiving end voltage, this is a midpoint voltage, Vm, this is a vector representation, and then Vsm and Vmr, considering the sending it to middle point and then receiving to midpoint voltages, and plotting them. And if you try to take a plot of it, so this is this you can see P is equal to V square by X sine delta. This is the normal power transmission curve. Now with this fax controller introduced at the midpoint of the transmission line, you can see that the active power has been increased by 2V square by X sine del by 2. So it has been doubled. It has been doubled, but at the cost of this much of the reactive power. So you have to spend this much of reactive power, then you will get this much of a power transfer instead of the simple this one. So this power transfer is almost double. It is almost double, and the reactive power requirement is this much. So who is taking the reactive power requirement? We are introducing some reactive elements into it variable. So with that, you are getting a double power transfer. Active power transfer is double now. So you can now clearly get convinced that the fax controllers are beneficial and they maximize the power transfer capability, and the location is midpoint. Now the first one is the TCR and the TSR, the Thyristor Controlled Reactor. And suppose a transmission line is used, like, so for example, I would like to just cover that point and then we'll go. If the transmission line is huge, then what will happen? You will divide into many halves. Okay, so you will divide into many halves, and then considering one half of it, and then at the midpoint of that half, you will be introducing the fax devices. So optimal location, you were asking me about the research area. So the optimal location of a fax devices and simulating it and seeing whether you are getting a really how much power is maximized can also be taken as the area of research. Now, the one of the type in a shunt is TCR and TSR, that is called as a Thyristor Controlled and Thyristor Switched Reactor. It's a lecture, so Thyristor Controlled and Thyristor Switched Reactor. So in this case, you can see now these are the bidirectional devices, switches. Okay, these acts as a switches. You know that these devices act as a switches, and we are adding inductor into the circuit. So this is a transmission line. You are connecting this reactor into the transmission line with the help of the switches. So the switches will be made on and off. The switches will be made on and off. The alpha, that is a delay angle. If you delay alpha is equal to 0 ideally, when alpha is equal to 0 ideally, then the IL will be like this. So the IL will have a 90-degree displacement, a quadrature to it, and it will be exactly the amplitude will be the same because the alpha is equal to 0, delay angle is 0. But if I further delay the switching of these devices, then the IL will change. IL will change, and this shows you that how the magnitude. This is all fundamental component we are looking at it. So how the magnitude changes of the IL with the change in the alpha. Okay, so this is the basic operation of Thyristor Controlled Reactor and Thyristor Switched Reactor. Okay, so generally currently available thyristors are like they can block the voltages up to 4,000 to 9,000 volts and more than that, and even they block the current to the range of 4,000 to 6,000 amperes. Okay, so this kind of a controller, which is a very simple one, TCR and TSR, you can use as a fax controller. Now, another important thing is that the valve, the switch is automatically turns off at the instant of the current zero crossing. Okay, so whenever there is a zero crossing, it will automatically turn off. Okay, so this is about it, which we have seen now. Now, how will you limit the voltage and the current, like operating VI area of the TCR and the TSR? So this gives you the area of Thyristor Controlled Reactor and Thyristor Switched Reactor. So this gives you this line. This line will decide the operating VI area, operating area on the VI curve. Okay, so this way you can change this area. You can change this BL, and this area can be changed. Okay, so this BL is the admittance reactor. BL max is the maximum admittance of the TCR, current limit and voltage limit. So it depends upon the system. Then another very important fax controller in a shunt category is the TSC, that is called as a Thyristor Switched capacitor, which is very popularly used. Now again, those who are trying to do the research, they can do the research on any devices, any controllers, because I'm just focusing on the basic controller working, like the fax controller working, principle of working, and their topology. I'm focusing more on this. But whenever you try to implement it with some problem, like the use of a TCR and TSR for power quality mitigation, like if you look at the electric arc furnaces, so electric arc furnaces is densely populated in industry, because the furnaces are required in industry. Any industry, there will not be any industry who will be working without furnaces. So furnaces, when they run, they take a lot of huge amount of current at the beginning, at the starting, and that creates the sag into the circuit, and the sag has to be mitigated. So you can think about such controllers to mitigate the power quality issues. So generally the STATCOM is preferred and all, but those who want to do the research, they can think something out of box, and they can think about this controller as a power quality mitigating devices or controller, or they can consider it as a even apply in any now microgrids also. So you can think about such areas. Now the Thyristor switch capacitor is also very simple one. What will happen? With the switching of these two switches, you will be introducing this C into the line. You will be introducing this C into the line. You are introducing capacitor into the line, and whatever surge current will be there because of the introduction of the C into the line, that will be limited by this inductor L. So L will basically limit the surge current, and C will be giving you the voltage which will be in quadrature with the line voltage. So thereby what you are doing, you are trying to mimic the idea of reactive power compensation, and thereby you are trying to change the X of the line. Okay, you are not directly putting any component into the permanently into this line, but you are switching it on and off, and thereby changing the X of the line where it is connected in parallel, this controller, and you are achieving the less X, reduction in X, and thereby maximizing the power transfer over the transmission line. Now, if you look at this diagram, you can see that the V, the voltage, then the VC will be charged. So for positive half cycle, it will be charged completely, and the VL will be this, because VL is used for only limiting the current. So you know that the inductor will not allow the change of current so fast, and if you look at this, then the TSC is off and then TSC is on. So when the switch is on, when this is switch is on, means this is short, there the C is connected. When switch is off, the C is disconnected from the line. Okay. Now, whenever there is a switching, then you have to be careful. So when this capacitor is to be switched, because what can happen when you switch on the capacitor, the switching transients will become important. They become significant. So you have to reduce the this switching transients. Okay. So to reduce that, the switching of the capacitor is to be appropriate. The switching of the capacitor needs to be appropriate. So you need a transient-free switching. You need a transient-free switching of the capacitor. So for that, this is the condition. So if we see the capacitor voltage, the residual capacitor voltage is less than the voltage, is less than the line voltage, then what happens? You can switch it off when VSW is equal to, you can switch it off when it crosses the VC. So this point where you can switch on the device. Okay, you can introduce the capacitor into the circuit. When the VC is higher than the V, then you can switch on the capacitor when VSW is minimum. So you can switch on wherever it is minimum. So there you can switch on the capacitor. So it will be at the peak of this AC voltage. So this will ensure you the transient free switching of particularly thyristor switch capacitor. Now there is another one which is called as the fixed capacitor Thyristor Controlled Reactor type VAR generator. Okay. So here you can also see with this topology is that there is a fixed capacitor. Okay, the capacitor is fixed, and you will be only changing the L by switching of these two devices. Okay, so this is hence it is a fixed capacitor, and it is if you look at it, the operation will be quite you can say simple, because the C is fixed. So what you have to do, you have to study the transmission line, the reactive power compensation kind of a thing. So you have to consider that how much reactive power need to be pumped into the line. So accordingly, you have to make some part fixed and some part will be variable. So why it is required? Because at the demand side, at the load side, there will be always a variable reactive power demand. Like for example, there is a load at the other end of the line, and the load is continuously varying. And the load is varying means the reactive power demand is also continuously varying. Sometimes it is there is only lighting load acting, so the reactive power will be raised. But sometimes there will be a motors running, so the reactive power will change. So you have to identify from the data collected from the load demand what is the constant reactive power required. That is to be given by this C, and the one which is variable over that constant will be given by this part by switching L into the circuit. Now here there is a lot of research can be involved, how to develop the control system for such thing and how to analyze the data. Okay, so data analysis is also very important. So now those who are interested in the new concepts like you can say the data analytics and all, so they can have the you can say the interconnection of a data analysis block with the control system of this thing. So you can introduce some kind of a machine learning for this. So now you look at this control system. So it requires the three basic blocks. Okay. So this control system, like to control the introduction of this inductor into the circuit, you have to develop three blocks. One is this synchronous timing circuit. So you need a synchronous timing circuit. You need the conversion of a current to delay angle, because the angle, this alpha is required for this. Then you require the third block, which is the fundamental reactor component. So that is computed. The fundamental reactor current is computed. And the fourth function you need is to find out the firing pulse generation, which sequence it will be. Okay, so that it will go to this devices. So there are four functions are required. One is the synchronous timing circuit. Then you have to find out the current to delay angle. Then find out the fundamental component of reactor current, and then the thyristor firing pulse requirement. So this way the control system works. So you can see that the reference is IC, and the IQ reference. Then this will give you the current to this admittance block, which will be converting into the delay angle. Okay, so this way you have to establish a control system, which is very important, because functionally you have understood, but you need to trigger this or fire these devices at correct instances and with the correct frequency. Now next is the Thyristor Switched capacitor and Thyristor Controlled Reactor type bar generator. Okay, so now it is little different from the previous one. One second. So it is a little bit different, because it is different because here the capacitive and inductive, this part will be controlled. This part will be controlled by the controlling of the triggering of this devices. Okay, so this actually gives you the dynamic compensation of power transfer system with the intention of minimizing the losses, and it increases the operating flexibility, because you can change. Now you can move over this line. You can move this line. So you can understand like how much is the capacitive and how much will be the inductive part to be required. Okay, to get the maximization of a power transfer theorem, power transfer over the transmission line. Okay, so you can make the various parts of it. Okay, so what you can do, you can make such a part like I'm extremely sorry, there is a this diagram is not correct. I will give you a diagram. I will show you the diagram quickly. Wait. So this diagram is not correct. Yeah, we have to switch the capacitor, and thyristor has to be controlled. So I will draw it quickly. So my screen is visible, I think. So it will be simply like this. So this capacitor will be, I'm just putting the switches over here, you can understand. And so it will be like a series of such, and then one you will have a reactor. So it will be like this. Okay, so you will be switching. So these are the numbers. These, how many arms should be there? How many such branch should be there of the thyristor switch capacitor will be decided by the Q requirement. Will be decided by the Q requirement of the line. So it will be connected in parallel to the line or in shunt with the line. So this will be the IQ flowing through it, and this will be IC1, IC2, and this will be something IL depending upon the alpha. So as you change the alpha, the IL will go on changing. So this is the thyristor switched capacitor, thyristor controlled reactor. So you might have understood that why it is called as a switched capacitor, because the thyristor is fixed. So thyristor is only getting switched. But here the inductor, it is getting controlled because you can change the value of the flowing through this, the current flowing through this with the alpha, with the variation of a alpha. So you can change the inductive and the capacitive part of the circuit. So this, so you can now, as a research, you can, the first is determination of number of branches. Determination of number of branches. So how many number of branches I will be requiring? This is one thing. Then the another thing is that control the switching of tails, this branch. Whenever there is a capacitive switching, okay, thyristor switched a capacitor, it should be transient free. So you have to design a control system, so which will give you the introduction of a C into the line, which will be transient free. So the switching transient need to be reduced. And the third is the variation of a current. Variation of a current in the thyristor controlled reactor by firing angle. By firing angle. So find out the appropriate angle, delay angle or the firing angle, which will decide the current flowing through this TCR. Okay. So there is a two part. One is the TSC and the other is a TCR, and hence the control system becomes very important into this. And these are the areas where you can work. So you can take an application of TSC, TCR for any challenge like a power quality issue mitigation or the reactor power compensation or the power factor improvement, something like that. And then you can think about on these parameters. You can work on these three parameters and you can make the system. So this is about the thyristor switch capacitor and thyristor controlled reactor type power generator. Now you can see how the control system will be there. So there are two parts which I told you: thyristor switched capacitor and thyristor controlled reactor. So it will have a required capacitor and required reactor current computation. So you need a block which will compute the capacitor and reactor current, and then this will act as the input. This will act as an input to these two controls, which will be on-off control, and this will be the firing angle delay control. So this will generate the pulses for this thyristors, for this switches, and this block will generate the pulses for this. So this can be a PWM. So those who are from electronics background can work on the switching phenomena, like how the switching can be done and how the switching can be more efficient and effective. So this was about the shunt connected controllers, which are impedance control. Okay, so what we are trying to do is that actually introducing the component. If you look at this, we are actually introducing the component into the circuit. Okay, but now we will be looking at the switching converter type power generator now. So here we are not introducing any component into the system. But it will work as mimicking the idea, like by changing the converter firing strategy or triggering strategy, you will be introducing the reactive power into the circuit. So this is basically compared with the synchronous machine. So in the synchronous machine, what happens? The overexcited machine works into a leading power factor, and then the underexcited will work as a lagging power factor. So in overexcited, it supplies the reactive power in positive reactive power, and in Underexcited, it generates a negative reactive power. So the similar concept is used, and then instead of a synchronous machine, we will be using a converter. So there is a DC capacitor over here as an input side. Then it will convert this DC to AC converter will convert the AC. The AC generated out of this converter will be in such a way that it will be introducing it in a phase quadrature to this line bus or the system bus. So you will be actually mimicking the idea of introducing any reactive element into the circuit, because when you introduce any reactive element, like when you introduce the capacitor or when you introduce this inductor into the circuit, what you are doing, you are maintaining the phase quadrature relationship, which you are now mimicking through the operation of the switching converters. So you can work on these various topologies of this converter. So there are various topologies. Now the popularly used are the 6 devices. Okay, so you can think of a multi-level inverter kind of a things, and let's have a look like what happens to the overall control system or overall improvement into the system for power transfer or for the mitigation or for the power factor improvement. So for any application. So this can be also, you can look at it as an area of research. Now look at here what I was trying to explain you, that this is a particularly VSI because the input side is the voltage source. So capacitor will form a voltage source, and the output is now the AC which will be connected to the bus. Okay, so now you can see whenever it is connected to the bus, you will be connecting it to the coupling transformer. So the coupling transformer reactance or inductance, leakage inductance will obviously give you the complementary to this C, complementing to this C. So C is there, so automatically you are getting this L. Hence, the VSI is preferred over the CSI. If I would have been used here the current source inverter, then here it would have been the inductor as a source, because I need a current source. So there might have been the inductor. So inductor value would have been also very huge, and handling the DC capacitor is easy than the inductor. Okay, and then you would have got here. You have to put additional capacitor over here because to complement this too, and then this will become a bulky. Okay, hence the VSI, that is the voltage source inverter, is preferred over the current source inverter. Now there will be 2 control loops required. One is for the internal control loop that will be required for a converter. Okay, so you can have so for converter, you can here the converter can be a single phase edge bridge, it can be a 3-phase, a 2-level edge bridge, or it can be multi-level, I said, and then this thing also 12 devices. So you can have various topologies, or you can devise some other topology which uses a less number of devices, less switching, something like that. So those who are interested in power electronics can work here for identifying the various topologies, because these topologies are also affects the impact. It impacts the power quality at here also. So you can work on this converter. Now the internal converter controller will require, and that controller will be taking a IQ reference and IP reference, and then it will be generating the output voltage, magnitude, and angle computation. Okay, then gate pattern generator, and the gate pattern generator will be given to the converter. So you need a one control system here for a gate pattern generator. So the gate pattern can be PWM based, or you can select the thing. So this is one control loop. The another bigger control loop is required outside this. So you need a reactive current computer, then how to compute a reactive current. Then it will be compared with the reference, how much you need, because you know that whenever the power system is there, if it is a short of reactive power, the voltage, it will collapse the voltage also. Voltage will collapse, and then the system can collapse. So if I add more voltage into it, then the frequency may collapse. So we have to have a proper appropriate amount of IQ. So this IQ reference computation, and then it will be compared. This will generate the alpha set point, and then with the phase lock loop, which is synchronized one, we'll get the actual theta, and from this the gate pattern will be generated, which will be given to the converter. So these are the two loops which will be working in a cascade. So you have to apply the cascade control loops here, and when you apply the cascade control loops, you have to give a thought upon the dynamics of an inner loop and the dynamics of the outer loop. Okay, because the outer loop is giving the set point for the inner loop. So outer loop is slow, then it will not solve the purpose. Outer loop dynamics has to be fast, so that it will create a set point, and then internal loop will give the gate pattern. So you have to, whenever you design a control system, you have to keep this in the mind. So this is about the which is called as very popularly called as a STATCOM. So whenever there is a fax controller, everybody thinks about only STATCOM, but it is not like that. STATCOM is a powerful switching category, like in a switching category, it is a powerful shunt controller, but there are others also. So depending upon the application, depending upon the situation, depending upon the requirement, you should select the fax controller. Now the another is the SVC, which is also very common. So which is called as the static var generator observer or absorber, which we have studied till now, various SVC. Now the next comes is the series connected controller. So here you will be connected in series. So obviously it is said that the shunt is basically outperforms the series connected. Now there are some good articles wherein why SVC, the static var compensators and the STATCOMs are compared, wherein the STATCOMs seems to be more better in terms of you can say the control system, because you can get transient free and there are various parameters on which you can compare them, but the harmonic generation and all is very less in terms of STATCOM. It is only high in terms of a fixed capacitor, because what happens, the fixed capacitor will give you will not be able to will not help us to reduce the harmonic levels. So harmonic levels can be controlled in a STATCOM very effectively. Then the losses are also very less in terms of a STATCOM, because in STATCOM we are not introducing any reactive element into the line as such. We are mimicking the concept through the converter. By the converter is giving the voltage which will be in phase with the line voltage, the current and voltage which will be in phase quadrature with the line voltages. So we are not introducing any element access, so the losses are reduced, and then you can see the VI and VQ characteristics, which will be better in terms of a STATCOM than SVC. So whatever SVC we have seen, no. And like any system, there will be a damping, there will be oscillations, okay? Because if you give sudden input, because this will be introduced into the circuit, so it will generate some oscillations. So in STATCOM, the control is better. In the other SVCs, the control is little poor. So in control point of view, and in loss point of view, and in harmonics point of view, the STATCOM outperform, right? But it doesn't mean that for every solution or for every challenge you should go for a STATCOM. It might happen that for some problems, the other SVCs also can work, because whenever we try to give any solution in terms of for a power system, then it should be economically viable also. So sometimes a very simple system which can be worked with a fixed capacitor, TCR kind of a thing, because you know that the data of reactive power generation is fixed for some period. it's continuously fixed for some slab, then the fixed capacitor will give you the better results, and because the maintenance will also be better in that case. Now we'll go for a series connected controller. So in series connected controllers, again there are three types, which are the impedance changing type, and the other one is a switching type. So in GCSC, you can see that now they are connected in series. They are connected in series. So the capacitor will be connected, but here the GTOs are used. You can see here the GTOs are used for their own reason, like they have the commutation properties. And this voltage stability is also very good in terms of series compensation. Okay, so it improves the transient stability, voltage stability, the series compensation basically, and the power resolution damping is also observed to be good in this series compensation. Then you can see now from this GTO. So basically the objective of GTO is to control the voltage, the AC voltage basically across the capacitor at a given line at any current like I. So when the switch is closed, the capacitor voltage will be 0, and when the switch is open, it will be maximum, because you know that when switch is open means the whole voltage will enter across the capacitor, and when switch is closed means it is as good as the short circuit, so it will be 0. So this kind of a scheme is used and will be used in series. So the control diagram for this will be like this, wherein the voltage of capacitor will be the reference, which will generate the gate pattern, which will generate the firing pattern for this devices. So this will receive the timing circuit, the synchronous timing circuit, which you give to the PLL, and the capacitor voltage sensing and processing circuits. So these are the blocks required in a control system of triggering this bidirectional devices to introduce C into the line for the reactive power introduction. Now there is another one is called as a Thyristor Switched series capacitor. Thyristor Switched series capacitor. Now you can use so many units. So Thyristor Switched series capacitor here. So instead of GTO, now it is a Thyristor, and you can use number of units depending upon your requirement. So this kind of you can make a complete system. You can design a complete system. So those who are doing the research, they can think of designing a complete system for TSSC. So what happens, like you can have a five units such design, and depending upon your reactive power generation, you can only activate 2-3 units as per the requirement. So this is very easy to say in English, like operate only 2-3 units, but you have to develop a control system which will take care of this. So that always the control system is very, very important. So designing a control system. So those who are from a control background can think upon a supervisory control which will control the firing of any one of these units. So this will be connected in series. Now the next is the Thyristor Controlled Series Capacitor. Okay. So here you can see now the LC circuit will be formed here. So whenever there is a LC circuit, so you can understand that there will be a possibility of a resonance. Okay. So you have to select the components LC such that the resonance should not happen. Okay. And so the impedance of the reactor XL, which is here, like the impedance of the reactor which will be XL, should be sufficiently smaller than that of a capacitor. It should be smaller than the capacitor. Then what happens here? The C will be completely into the line, connected to the line. What you will be changing? You will be changing the IL with IL, variable IL. And how? By changing the switching of this, by switching on and off these devices. Okay. So this is the working of TCSC. Okay. And this gives you the the controls block diagram. So in the control block diagram, you might have understood till now is that you need always you need some delay angle converter, the computation block which will calculate the delay angle, which we will be giving through the gate pulse generator to the devices. Then you need a synchronous circuit. Then you have to compare the VC and VC reference, because now here if you look at the C is fixed. Okay, so you have to maintain this VC at the required level, and how it will be maintained by this L. So you have to always compare the VC and VC reference, and then by taking this VC and VC reference, you will be generating the gating pulse. So this is the control system required for TCSC. Now this is the another control system which is explained for TCSC, and basically this gives you you can say this is little if I go back, this is simply giving you the like this is the control system based on the basic operating principle, and this is a control system which will be giving you on the synchronization of the fundamental component of line current. Okay, so a little difference. So what is the difference is that we have introduced the controllable phase shifter and the angle correction units into this. So you can find out the fundamental component. So this will help you to reduce the harmonics and even the transient switchings. So this is the little advanced over this. Okay, but the principle will remain the same. Now here also in this series also there will be a switching converter type series capacitors, where again the same principle is that you will be introducing the effect of adding of a reactor into the line by using a converter. So which converter is used? Again, the voltage source converter is used. Now the energy source is optional, because you can have the energy source as a SME, that is superconducting magnetic energy storage, or the battery, any source, energy source, DC source you can use for this to charge the capacitor. Because this side there should be a DC, and this side there will be AC. So DC, for getting a DC, you can use any source like SME, battery, any energy storage you can use. Okay, and then this will be injected. As a research, you can use any renewables also, and just see how you can design the system, because you need a DC only at this end. So DC can be taken from any system. Now we'll move to the next. This is called as a SSC, which I have explained you. It is like only STATCOM, and only thing is that it will be connected in series. The STATCOM is connected in parallel. Okay, so this is the control scheme for the static series compensation, wherein again you need a gate pattern logic. So there will be again two loops which will be cascade. One is to generate the alpha delay angle, and delay angle will be generated by the reactive power requirement. Okay, so the VQ will be taken, the Q component of V will be taken, and that will be creating a reference for this. So whenever there is a two loops, you have to consider the time required to execute the outer loop and the inner loop. Okay. So now next is we will see the combined shunt and series connected controllers. So there are two types. Initially we have seen that is a unified power flow controller, which is very popularly used, and the interface power controller. Now particularly these kind of controllers are considered as a connected controllers, because the two different types of a fax controller you are connected together, and then through that you are trying to achieve the maximum power transfer capability. Okay, so if I go ahead, so this is a simple one that is called as a combined series and shunt. This is very popularly used, unified power flow converter. Now basically if you look at it, you will find that this kind of a controllers, when I say it is series and shunt connected, or the connected controllers, basically they gives you the flexibility of exchange of reactive and real power both. Okay, in a previous all examples we were talking about only reactive power exchange, because we are not increasing any we are not exchanging any active power through it, right? Only we are trying to inject the reactive power, so that the X has to be minimized, so that the power transfer will be maximized. Okay, but now in this case, with the interconnection of the two controllers or two converters, fax controllers, two types of fax controllers, you can exchange the real and the reactive power. So this has got the capability of exchanging the real and reactive power both. Okay, basically the unified power controller is introduced by the Gyugi. So this Hingorani and Gyugi, they work together and they have developed these various fax controllers. Okay, so this is particularly introduced by Gyugi in 1991. Okay, so it is basically used for providing the flexibility for power transfer. Okay, so we'll see the basic principle of operation. One second. Right, this will be, so here you can see the topology, and then we will see the principal operation. The topology is that here it will be a series controller, and here it will be a shunt controller. So here I have shown you both of the switching kind of a type. One is the SSC, the static series capacitor, and this is the STATCOM. So in this case, these two controllers are tied together with a common DC link. These are tied together. Just remember, these are tied together by a common DC link. So they are unified together by this DC link. So that's why they are called as a unified power flow controller. So this is a line, this is in series, and this is in shunt. Now, if you look at the block diagram over here, you can see this converter 1 and converter 2. Okay, so one is in series, one is in you can say parallel, and the converter one, the operation of a converter 1 and converter 2 will help us to establish the power flow, like the amount of a power flow, the reactive, real power, and the reactive power. Okay, so the real power can freely flow in either direction between the AC terminals. So real power from here. So they are, you can see that they are connected to the AC side from this. Okay, so the real power can easily flow from this side in these two converters, and each converter independently can generate or absorb the reactive power at its own output terminal. Okay, are you understanding the beauty of this? Is that as they are connected together by this DC link, and they have a common connection here at the AC side, so the real power they can exchange through this AC line, and by the gating pattern of converter 1 and 2 with this control system, because this control system will give the gating pattern till now what we have seen is, how you generate a gating pattern by comparing the reactive power and the reactive component of voltage and current, and then you generate this gating pattern. So by this gating pattern, this converter 1 and 2 independently can generate the reactive power as you desire. Okay, so there is a both real power exchange as well as reactive power exchange. So this topology or this arrangement will maximize the power transfer, and even not only maximize the power transfer, but this gives you the better dynamic stability and the you can say the flexibility also in power system. So this was about the UPFC. Now we'll go to the interline power flow controller. So interline power flow controller is also similar to the UPFC, which are tied together, connected together, or controller connections. The controllers connected together, but it's a little different from the one which is UPFC. So how does it differ? You can see that both the controllers are connected. Both the controllers are connected in a series. Okay, so there will be a static synchronous series compensators are connected, and they have a different they have a separate converter. Okay, so every line will have a separate converter, and then the controller will be a common. So their controller will be a common. So basically, IPFC is like it also allows to flow the real and reactive power both between the line. Okay, between the line. So it is little difficult, little different. I mean, because every controller. So this is the one line. Then you can imagine there's another line. There's another controller, converter and controller. And the controller can be a single one. Okay, so you can put many IPFC together. So this also gives you the flexibility of real and reactive power compensation both, like reactive and real power controlling both. And IPFC is also popularly used. And here we have used the static SSC. You can use you can try using the other controllers and do those studies also, those who want to do in research. So the other type of controllers are like Thyristor Controlled Voltage Limiter, Thyristor Controlled Voltage Regulator based on tap charging, Thyristor Controlled Voltage Regulator based on voltage injection. So basically, what is the major thing behind this is that you have to change the X. You have to change the X of the line, that is the reactance of the line, either by switching or by introducing the actual reactor into the circuit. So as I told in the beginning, that this involves the power electronics, this involves the control system, and obviously the power system studies is required because to compute the reactive power requirement and the other real power requirement. So I would like to stop here, and we'll take some questions which you would like to ask. So questions, anything you would like to ask?
Hello. Madam. Namaskar.
Namaskar, sir. Namaskar.
Sorry, I could not join in the initial.
No, it's fine, sir. Because I can understand you're joining. It's too much, like
No.
handling the charge of the institute and then joining. It's really.
Yeah, there are so many administrative issues. And
Yeah, I can understand.
असतील ना अँकर आमचे
तुमचे अँकर
Yes, sir. Yes, sir.
मॅडम नेहा मॅडम इथे
आहे.
Yes. So
Okay. Yeah. So questions. Somebody was asking me something like this, so we can take questions now.
Participants can ask questions.
Good afternoon, ma'am. May I ask one question?
Yeah, please.
Ma'am, practically, if I need to work on the designing of this controller, will it be DSP based always?
Yeah, not always. You can use any processor, right? Not required. Like you always go for a DSP because if your computations can be handled by any other processor, that is also fine. So you can look at the kind of a computations you would like will be involved and then select a processor. So many microchip processors, peak processors also can be used. Like you can develop around that.
Okay, ma'am. And ma'am, when these fax devices are there in the system for steady state operations,
Okay.
and 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 if any instability occurs like fault and all, the protection circuit for these devices are to be designed for by taking in some other criterias or what, ma'am?
Yeah, you have to take care of those things. Like suppose on a transmission line, suppose there is a fault is occurring, then you have to like use some protection system. But particularly for the fax controller which we are looking into, the series and shunt, there you can have our own systems. If you are looking into the whole power system, then it will be a different. But for fax controller,
for individual, no, ma'am? Yes,
yeah,
yes.
for individual.
Okay,
That's
okay.
why we said that we have to select the devices which will have a dV by dt and di by dt, which will be suitable to your power system requirement. Suppose any fault occurs and the huge current, there is a huge di by dt, so it should be withstand. Okay.
Yes, ma'am. Yes, ma'am. Thank you very much. Yeah.
And basically, this fax, basically, if you would like to work in a fax, then lot of things you can do in a control system, because the identification of a controller, because what I have shown is the block diagrams, right? But if you want to really use a controller, then you have to think about a non-linear controllers also, because whenever you design a controller, you need a mathematical modeling of the system, right? Whatever
Yes,
I was
ma'am.
talking
Yes, ma'am.
today was talking in terms of only blocks, right? But every block has to be represented in a mathematics, and that mathematics will represent the dynamics of a system in terms of a differential equations.
Yes,
And
ma'am.
then you have to think about which kind of a controller I should use. So conventional controller like PI, PID can be used by linearizing it. So then it will be a sensitive for a particular operating point only, right? Suppose if
Correct,
I
ma'am.
want
Yes.
to use for some reactive power compensation of some VAR, for example, I am using 20 VAR generation only. So my system will be working plus and minus 20. Okay. But if I use a non-linear controller, then I can go with a little bigger bandwidth, right, of the set points. So lot many things can be done in a control system also. Lot many things can be done in a power system, power electronics also, in a converter design. So giving thought to a different topologies and different devices. Now you all know that GAN kind of a devices has come, which gives the less losses. So you can think of simulating the things with those devices and finding out the losses and comparing it with the convention.
Yes, ma'am. Thank you very much. Thank you, ma'am.
Ma'am, myself Sahasran Sudas. Hello.
Yes, yeah.
One question, ma'am. I'm area. Hello.
So
I'm
your voice is breaking.
hello. I am working in stability areas, madam. Actually, the mob which is connected parallel with your sound compensations,
Hmm?
and what is the range of that mob? And second one is, what is the air gap which is connected parallel to this mob? What is the necessity of that air gap? And
I, extremely sorry, I could not get your what word you are using. I am not getting it.
actually, madam, in sound bar compensations, a
Okay,
mob
shunt compensation, right?
compensation
Hmm.
across the capacitor, a mob is connected, metallic oxide Thyristor.
Okay. Huh.
And that mob is a power electronics device, and it restrict the voltage across the that shunt capacitor. And second one is, what is the justification of air gap which is also connected parallel to that mob, and
Yeah,
which is
I have not tried with such a device. I am not really getting your topology. Are you using a MOSFET or something? I am not getting it.
no sir, madam, this is a MOV.
MOV, okay. So where you are using MOV? Because I have not done such things. Where you were using?
Actually, which that is connected parallel with the shunt capacitor,
Okay,
and it restrict the voltage at a transient condition or dynamic conditions. The
okay,
voltage across the capacitor is too much high, it may
okay,
break the insulations. For
okay,
that, the mob is used. And
okay,
second one is, here a air gap is also connected parallel with that mob,
okay.
and that range also varies. And how will get that range? In which
Uh,
capacitor, what range of that air gap we connected, and what is the function of that air gap? And this air gap also connected with a circuit breaker.
yeah, but I'm extremely sorry because I have not worked to that level. I am working basically on a power electronics and a controller. Okay, so this you may please contact any power system person who is working into it. Hmm? So, or otherwise, I will look into it and I will get back to you.
Okay, ma'am.
Hello, madam. I am having one query. Madam, actually, if I want to compensate active and reactive power in three-phase transmission line, so whether I have to install 3 UPFC or I have to install 3 STATCOM?
You have to like no. UPFC and STATCOM are the different.
Yes, ma'am. Because actually, UPFC is a combination of that STATCOM and triple SC.
Right.
So when so according to that, according to efficiency point of view, so which one is more suitable, STATCOM or that UPFC?
The STATCOM, so depending upon the problem, like suppose your reactive power compensation is not so complicated, then you can go for a STATCOM only, right? But if you wanted to have a real power control also and a reactive power control also, both the control you would like to have as per your load, so then you can go for UPFs.
So ma'am, in that case, actually, if you are having a 3 phases, so for 3 phases, you will have to install then 3 STATCOM.
Right, 3 STATCOMs.
Okay.
Yeah.
Okay. Thanks a lot, ma'am. Thanks a lot.
Good afternoon, ma'am. Am I audible, ma'am?
Yeah, you are audible.
Ma'am, can you suggest any other simulation tool for fax controller, ma'am, other than MATLAB?
Other than MATLAB?
Yes,
okay.
I'm using MATLAB right now, ma'am. Is there any other simulation tool?
Not as such, but for power electronics, you can try PCM because that helps us. Like that gives you the direct. There are many blocks available, so you can think about it. But
okay.
I have not tried it other than the MATLAB.
In MATLAB, in simulating, some libraries is there available. It is available.
Yeah.
Fax devices are available in Simulink library.
But he wanted to see something different from MATLAB Simulink, right?
Yes, ma'am.
So
Something different from MATLAB.
PCM you can see, PCM you can try. Or now many people are using some other open sources also, so you can try that. But PCM can help you for power electronics, because PCM and MATLAB, they get connected now. So you can import those power electronics into the MATLAB, like if you want to.
Sure, ma'am. I will try out, ma'am. Thank you, ma'am.
So I hope there are no more questions. Madam, we are very thankful for this wonderful session that covered basic and detailed knowledge of the controllers of facts with their location. Also, we have seen the design aspects of the where we should place the where should we decide the locations with mathematical analysis, and how we have to design the transmission line for maximum power transfer. So it was very informative session, and we are very thankful and glad to have your session. Thank you, ma'am.
Yeah, thank you very much. Thank you each one of us for listening, and
Thank you, madam.
And also,
thank you, madam, for accepting our invitation, and you have given your important time for us. And really, I